Now we're going to look at the wave equation in a simple classical system, which is a wave on a string. And I have here a small guitar. This one's called a ukulele. It's a little 4-string guitar. And it's got various strings on it, as you can see. And of course, if you pluck these strings, they make notes. And we're going to be looking at the equation that describes waves on a string and therefore how you get the different notes. Now, to do this, we're going to look at very simple solutions. That is what we could think of as the standing waves that we could have on such a string. And those are actually made up from traveling waves going in two opposite directions, involving reflections off the two ends here. But we're going to solve this problem directly. Now, note a couple of things about the strings in this guitar. Typically, to play lower notes, the strings are actually a little thicker. You probably can't quite see that here, but the higher notes are usually produced by strings that are a little thinner. And also, there's obviously a tension on the string here. And if we change the tension, say you slacken it off here, as we slacken the tension on the string, the note gets lower. Now, let's look at how we're going to describe waves on strings like these.
To construct a classical wave equation, we can start by thinking of masses on a string. So the idea here is we have some set of masses and they're connected by a string, and the string is under a tension T. So for this mass here, the string tension is pulling it in this direction and also pulling it in this direction. And perhaps it's also pulling it up and down because these are at an angle. So we're imagining this is part of possibly some wave on a connected string of masses. So we have our set of identical masses connected by a string under a tension T. The masses will have some vertical displacements compared to some horizontal line we might draw here. So yj for the jth mass, yj minus 1 for the j minus 1th mass, yj plus 1 for the j plus 1th mass. And the string will be at some set of angles relative to the horizontal, so we'll call this one theta j minus 1, and we'll call this one theta j. Now, there's a net force here from this tension that is pulling the mass up from here, and that is T sine theta j. That's the component of this force that is in the vertical direction pulling upwards on that mass. Similarly, there's a force from this tension over here and this angle, a resolved component of this tension that is pulling the mass down, and that's T sine theta j minus 1. So this component here is T sine theta j minus 1 pulling the mass downwards, this mass here. So the net upwards force on mass j is T sine theta j minus T sine theta j minus 1. Now, for small angles, we presume we can approximate the sign by just the angle, actually. So this angle theta j for small angles is just the ratio of the vertical to the horizontal. So it's this distance vertically here divided by the delta z. And similarly, for sine theta j minus 1, it's this vertical distance here divided by delta z again. So this net force that we'd written down in terms of sines, that was pulling this mass upwards, becomes, with these simplifications, just these little formulae here. And of course, we can add all that up to get the net result of all of that. Now, you may recognize that, what we have in here. And indeed, in the limit of small delta z, the force on the mass, all of this stuff here, times the tension, the force pulling it upwards. We can put in a different delta z on the bottom, an additional one to get delta z squared, put one up on the top to compensate for that. And this here we recognize that in the limit of small delta z, this is just the second spatial derivative. That's the formula for the second spatial derivative when we take delta z down towards 0. So this net force upwards on the mass is the tension times the delta z here, which we're still thinking about, we'll keep that there for the moment, times the second derivative of the position vertically as a function of position horizontally. Now, note that with this expression here, we are saying that the force F on this mass is proportional to the curvature of the string of masses. So the second spatial derivative is the curvature. And that means, incidentally, that if these masses were all in a line, there's no net vertical force on the center mass, which makes sense. And indeed, if these masses were in a straight line, not a horizontal one, still there would be no net vertical force on this center mass. The amount that would be pulled up from the tension along this direction would equal the amount that was pulled down from the tension along that direction if all of these masses were lying in a line. So this net vertical force on this mass is proportional to the curvature. It doesn't matter what the gradient is in the string. So if we think of the masses in terms of an amount of mass per unit length in the z direction, that is the linear mass density, kilograms per meter, times delta z, the number of meters, we can think that these masses are really equivalent to some linear mass density times delta z. We'll call them m is equal to rho delta z. Then Newton's second law gives us that the force is equal to the mass times the acceleration, of course. And we're saying we're going to call this mass effectively the mass of one of these little objects. We're going to call it rho times delta z. So putting this together, we have one expression for our force, which we get from the curvature of the string, and this other expression that relates acceleration to force involving the mass here of one little string segment, which we imagine for simplicity is concentrated in this little mass. Putting them together, equating them, we get this obvious equation. Take this part here and equate it to this part here. In other words, dividing out by the delta z's, d2y by dt squared is equal to rho over t times d2y by dt squared. Rewriting this using v squared equal to t over rho, then we'll get an equation like this. And this is a classical wave equation. d2y by dz squared minus 1 over v squared d2y by dt squared is equal to 0. And this wave equation, as we can easily check, corresponds to one with a wave velocity that's equal to the square root of t divided by rho. So we can look at our classic wave equation solutions. We can check these out. We remember that any function of the form f of z minus ct is a solution of the wave equation, and it's a wave moving to the right with velocity c. And similarly, any function of the form z plus ct is a solution of the wave equation, and it's a wave moving to the left with velocity c. So we're just using c here as the wave velocity, which would be the v in our previous equation. Now, often we're interested in waves that are oscillating at one specific frequency, and we'll again use angular frequencies here for convenience, so we're oscillating at one specific angular frequency, omega. So that means we've got a temporal behavior of this form. It could be something proportional to e to the I omega t, or e to the minus I omega t, or cos omega t, or sin omega t. All of these would correspond to waves oscillating at a specific angular frequency. And indeed, we could make any combination of these because this equation is linear, so we can add up solutions provided they obey our boundary conditions. So we can write this wave, if we're presuming that it's going to be monochromatic, as some product of the variation in z times the variation in t. And if we do that, again on the presumption that we're dealing with a monochromatic wave, then no matter what combination of these we might have, d2 phi by dt squared would just be minus omega squared phi. And putting that into our previous wave equation would leave us with this wave equation here, which you see is only spatial. And note now, because we're only dealing in this particular case with one dimension in space, we can go back to writing these as total derivatives. So this is just our previous wave equation using this result, given that we're working with some monochromatic wave, we've chosen to do that, then our wave equation simplifies to this form, and k squared here is omega squared over c squared. Again, we're using c as the wave velocity, which is probably more common than the v we used in our derivation. And this equation is called the Helmholtz wave equation. It's one of the simplest wave equations, and we use it in classical physics when we have something that's a monochromatic wave, only one frequency. And we've just seen how we would simplify our wave equation using this simplification here to get this result.
So as I said, quite an important concept with waves is standing waves. And we illustrated what are standing waves here with this guitar string. This concept is particularly important in quantum mechanics, where it can actually lead to the idea of quantized states. Here we're going to look at it for a wave on a string, where the string is attached to both ends at walls. And here's one of the walls. It's the bridge up here of the guitar, and down here we've got the neck of this guitar, and the string is stretched between these walls, and it's pretty well fixed at these two walls, if we want to call them that. So we're going to be looking at standing waves in a string where a string is attached to two walls at both ends. Now, one other thing about this is that standing waves, there are various different standing waves you can fit in between the walls. You could fit in one that sort of looks like this, and it oscillates up and down, or you could fit in one that looks up and down again like this. And in fact, I might be able to illustrate that on the ukulele here. So I can pluck this string and get a note, and I may be able, it's quite tricky in the ukulele, I may be able to get what's called a harmonic. So if I lay my finger halfway up the string here, I'm going to force this string to have what we'd call a node, a minimum or a zero in the wave at this point. And if I can do this right, I may be able to get the higher octave, one octave, twice the frequency higher. So here's the original note, and maybe I can get the harmonic. There's the harmonic. It's twice as high compared to the original one. So that harmonic corresponds to a wave more that is going up and down and back again, and the original note, it more corresponds to this kind of wave that just goes up and back, but it doesn't do this double cycle which I got on the harmonic.
Now let's think about standing waves. We take an equal combination of forward and backward waves. For example, we can take sine kz minus omega t, so that's a forward propagating wave, when we've got k is equal to omega over c, the wave velocity. And sine kz plus omega t is a backward going wave. Incidentally, we note that there's a trigonometric identity here that enables us to turn this summation into this product, 2 cos omega t sine kz. So that means that this wave that we're looking at, a combination equal of forward and backward waves, can be written as a product of something that changes in time times something that changes in space. This is always the same shape in space, no matter what the time is. So that's why this is called a standing wave. The shape of this wave appears to just sort of stand in space. Every point of it oscillates in time, but the spatial shape remains the same. So as I said, we call these standing waves. So we might think, for example, of a rope or a string tied to two walls. Here's a wall here and a wall over there. We've tied the string to the two walls, and this is one particular one of the standing waves that we could get here. In this case, we've chosen k is equal to 2 pi over L, which is the separation L between these two walls, and the 2 pi over L means that we go through a complete wave here as we go from one wall to the other. So that's why the 2 pi is in there. It gives us a complete wave from one wall to the other when these walls are separated by L. And that means that given k is equal to omega over c, of course, we're choosing omega is 2 pi c over L, where again, L is this separation between the walls. So this is only one possible standing wave we could get here, by the way. The key is we have to come up with solutions that give us zeros at both walls, but yet obey our Helmholtz wave equation. So let's watch it oscillate. Here it is, the standing wave. You'll notice that the shape remains the same, it just oscillates up and down in time.